Sure. Anyway, React as a UI runtime. Posted February 2nd, 2019. All the copies. 37-minute read. This is on overreacted.io by Dan Abramov. Okay, let's just scroll through all the things. Oh my, this is quite a lot of things. Okay, it's by, yeah, Dan Abramov. I explain with words and code. This is his personal blog. Let's go back to the top. Okay. React as a UI runtime. Most tutorials introduce React as a UI library. This makes sense because React is a UI library. That's literally what the tagline says. React, a JavaScript library for building user interfaces. I've written about the challenges of creating user interfaces before, but this post talks about React in a different way, more as a programming runtime. This post won't teach you anything about creating UI user interfaces, but it might help you understand the React programming model in more depth. Note, if you are learning React, check out the docs instead. Yellow exclamation point triangle. This is a deep dive. This is not a beginner-friendly post. In this post, Dan is describing most of the React programming model from first principles. Dan doesn't explain how to use it, just how it works. It's aimed at experienced programmers and folks working on other UI libraries who asked about some trade-offs chosen in React. Dan hopes you'll find it useful. I also hope that we will all find this useful as we do this live right now. Many people successfully use React for years without thinking about most of these topics. This is definitely a programmer-centric view of React rather than, say, a designer-centric one. But I don't think it hurts to have resources for both. With that disclaimer out of the way, let's go. Host tree. Some programs output numbers. Other programs output poems. Different languages and their runtimes are often optimized for a particular set of use cases, and React is no exception. React programs usually output a tree that may change over time. It might be a DOM tree, an iOS hierarchy, a view of PDF primitives, a tree of PDF primitives, or even of JSON objects. However, usually we want to represent some UI with it. We'll call it a host tree because it is part of the host environment outside of React, like DOM or iOS. The host tree usually has its own imperative API. React is a layer on top of it. Okay, its is pointing to Mozilla append child DOM API, and this is pointing to the iOS UI kit docs. So what is React useful for? Very abstractly, it helps you write a program that predictably manipulates a complex host tree in response to external events like interactions, network responses, timers, and so on. A specialized tool works better than a generic one when it can impose and benefit from particular constraints. Specialized tool, particular constraints, yes. React makes a bet on two principles. Stability. The host tree is relatively stable, and most updates don't radically change its overall structure. If an app rearranged all its interactive elements into a completely different combination every second, it would be difficult to use. Where did that button go? Why is my screen dancing? Dan's funny. I should hang out with Dan. Regularity. No jokes. The host tree can be broken down into UI patterns that look and behave consistently, such as buttons, lists, avatars, rather than random shapes. These principles happen to be true for most UIs. However, React is ill-suited when there are no stable patterns in the output. For example, React may help you write a Twitter client, but won't be very useful for a 3D pipes screensaver. Okay, we gotta click this now. Whee! Don't create this with React, maybe. Okay. Host instances. The host tree consists of nodes. We'll call them host instances. That does not roll off the tongue easily. Anyway, in the DOM environment, host instances are regular DOM nodes, like the objects you get when you call document.createElementDiv. On iOS, host instances could be values uniquely identifying a native view from JavaScript. So values uniquely identifying a native view. So they aren't actually the native view themselves, because that exists in the iOS runtime. And the JavaScript itself just sees a unique value that identifies that actual thing. Okay. Host instances have their own properties. For example, DOM node.className or view.tintColor. They may also contain other host instances as children. It's not easy to say. This has nothing to do with React. I'm describing the host environment and its environment. There's usually an API to manipulate host instances. For example, the DOM provides APIs like append child, remove child, set attribute, and so on. In React apps, you usually don't call these APIs. That's the job of React. Renderers. A renderer teaches React to talk to a specific host environment and manage its host instances. React DOM, React Native, and even Ink, what's Ink, are React renderers. What is Ink? Ah, cool. It's where your Ink is a tool to build terminal UIs with React. Okay, neat, cool. And even Ink are React renderers. You can also create your own React renderer. I have done this. It is fun, but they made it a lot easier relatively recently. So much easier now. Okay. For rendering things into Photoshop and stuff. John Gold, I think, made one that renders React into Sketch. That's pretty cool. Anyway, React renderers can work in one of two modes. The vast majority of renderers are written to use the mutating mode. This mode is how the DOM works. We can create a node, set its properties, and later add or remove children from it. The host instances are completely mutable. React can also work in a persistent mode. This mode is for host environments that don't provide methods like append child, but instead clone the parent tree and always replace the top level child. Immutability on the host tree level makes multi-threading easier. React Fabric takes advantage of that. Fabric. Blah, 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 blah. Fabric. Got it. As a React user, you never need to think about these modes. I only want to highlight that React isn't just an adapter from one mode to another. Its usefulness is orthogonal to the target low-level view API paradigm. It's paradigm agnostic, and orthogonality is, yes. React elements. In the host environment, a host instance, like a DOM node, is the smallest building block. In React, the smallest building block is a React element. May or may not be poorly named. React element is a plain JavaScript object. It can describe a host instance. JSX is a syntax sugar for these objects. Let's up the font size a bit so we can see all the things so much better. Maybe too big. Okay. Oh wait, too far. Okay. React element is a plain JavaScript object. It can describe a host instance. JSX is a syntax sugar for these objects. Button, class name, blue. Type, button, props, class name, blue. Okay. A React element is lightweight and has no host instance tied to it. Again, it is merely a description of what you want to see on the screen. Like host instances, React elements can form a tree. This is a syntax trigger for these objects. Type dialog, props, children, type blah, blah, blah. So dialog with a couple of buttons in it. Neat. Note, I omitted some properties that aren't important to this explanation. Ooh, some properties. Okay, we don't care right now. Maybe we'll care later. However, remember that React elements don't have their own persistent identity. They're meant to be recreated and thrown away all the time. React elements are immutable. For example, you can't change the children or a property of a React element. If you want to render something different later, you will describe it with a new React element tree created from scratch. Yes. I like to think of React elements as being like frames in a movie. Oh, frames now. That's not going to be confusing when talking about the web. They capture what the UI should look like at a specific point in time. They don't change. So like frames rendered into a like on screen, into your retina. Can't go back in time and change what you saw before. Yeah. Here, React elements. Snapshot of the view hierarchy at a certain point in time and space or whatever. Anyway, entry point. Each React renderer has an entry point. It's the API that lets us tell React to render a particular React element tree inside a container host instance. For example, React DOM entry point is React DOM.render. Render this element into this element. into this node. This element, yes, render this element into this node, DOM node. When we say React render React element DOM container, we mean, dear React, make the DOM container host tree match my React element. React won't look at the React element.type in our example button and ask the React DOM renderer to create a host instance for it. And React will look at the React element.type in our example button. So yeah, button or button, and ask the React DOM renderer to create a host instance for it and set the properties. Somewhere deep in the bowels of the React DOM renderer, simplified. We've got the React element, creating your DOM node, document.create element, React element.type, DOM node.classname, React element.prop.classname. Yeah. Yes. Okay. In our example, effectively React will do this stuff. Got it. If the React element has children elements in React element.props.children, React will recursively create host instances for them too on the first render. Remember. Reconciliation. What happens if we call React DOM.render twice with the same container? What is the container? This is the container. The DOM node container. Yes. So if you React DOM render this element into this DOM node container, and then later on, should this replace the button host instance or merely update a property on the existing one? What do you think? What should we do? Again, React's job is to make the host tree match the provided React element tree. That's it. React's job is to make the host tree match. Make the host tree match the provided React element tree. Okay. So if this is the provided React element tree, oh man, that's a mouthful. If this is the provided React element tree, and then this is the provided React element tree, DOM node.render is going to make the innards of this thing match the description described here, and then later on it's going to do the same thing, but with the descriptions here. So logically, it probably shouldn't throw everything away and redo it from scratch, because why would it have to do that? All right, make the host tree match the provided React element tree. The process of figuring out what to do to the host instance tree is, in response to new information, is sometimes called reconciliation. It's conciliation that you do twice. Reconciliation. Is conciliation a word? Huh, it is a word. Action of stopping someone from being angry. Huh. So reconciliation is to stop somebody from being angry twice. Okay, sure, why not? Okay. There are two ways to go about it, to go about React reconciliation. A simplified version of React would blow away the existing tree and recreate it from scratch, as described here. DOM container document.glmlid container DOM container.innerHTML equals empty string, thereby blowing everything away. Create the new host instance, blah, blah, blah. Do all the same things again, create the DOM node. But, don't do that. But in DOM, this is slow and loses important information like focus, selection, scroll state, and so on. Instead, we want React to do something more like this. DOM node equals document DOM container first child update existing host instance. In other words, React needs to decide when to update an existing host instance to match a new React element and when to create a new one. So should it create a new node or update the existing one? Host instance or DOM node or if it's UI kit, then whatever the UI view or whatever it's called. This raises a question of identity. The React element may be different every time, but when does it refer to the same host instance conceptually? In our example, it's simple. We used to render a button as a first and only child, and we want to render a button in the same place again. We already have a button host instance, so why recreate it? Let's just reuse it. Boom, done. Yay. This is pretty close to how React thinks about it. If an element type is the same, if an element type in the same place in the tree matches up between the previous and the next renderers, React reuses the existing host instance. Okay, when does React reuse the existing host instance? Oh, it's when an element type in the same place in the tree matches up between the previous and next renders. Oh, okay, thanks. Here is an example with comments showing roughly what React does. All this code again. Okay, now, can we reuse the host instance? No, because the button is not a P. Now it recreates it. So here, it makes a new one because the first time you're doing this. Here, it reuses it because it's the second time you're reusing it. It matches up with the previous render. Button. Here, it does not match, so it has to throw it away. Button to paragraph, you can't really do that. Here, we can reuse it because, boom, paragraph to paragraph. Boom, done. The same heuristic is used for child trees. For example, when we update a dialog with two buttons inside, React first decides whether to reuse the dialog, and then repeats the decision procedure for each child. Conditions. If React only reuses host instances when the element types match up between updates, how can we render conditional content? So we want to first show only an input, but later render a message before it. So first render, you got a dialog with an input. The second render, you have a dialog with an input, but there's a paragraph before the input. So now what? In this example, the input host instance would get recreated. React would walk the element tree, comparing it with the previous version. Dialog to dialog, boom, okay. Can we reuse the host instance? Yes, the type matches. Input to paragraph? Can we reuse the host instance? No, the type has changed. Need to remove the existing input and create a new P host instance. Nothing to input? Need to create a new input host instance. So effectively, the update code executed by React would look like old input node, remove it, make a new P, and append it, and then append a new input. But this is obviously stupid. So can we make React smarter? This is not great because conceptually the input hasn't been replaced with P, it just moved. We don't want to lose its selection, focus state, and content due to recreating the DOM. While this problem has an easy fix, which we'll get to in a minute, it doesn't occur often in the React applications. It's interesting to see why. In practice, you would rarely call React React DOM.render directly. Instead, React apps tend to be broken down into functions like this, where you get a bunch of stuff. This example doesn't suffer from the problem we just described. It might be easier to see why if we use object notation instead of JSX. Look at the dialog child element tree. Aha! Boom. The children. See this guy. These guys here become these guys here. Regardless of whether show message is true or false, the input is the second child and doesn't change its tree position between renders. If show message changes from false to true, React would walk the element tree, comparing it with the previous version. Dialog to dialog, can we reuse the host instance? Yes, the type matches. Null to p, need to insert a new p instance. Host instance, input to input, can we blah blah blah, yeah. And the code executed by React would look similar to this. Yada yada. Okay, no input state is lost now. Yay. Everyone is happy. Lists. Comparing the element type at the same position in the tree is usually enough to decide whether to reuse or recreate the corresponding host instance. Comparing the element type at the same position in the tree. Usually enough. But this only works well if children positions are static and don't reorder. In our example above, even though message could be a whole, we still knew that there was an input that goes after the message and there's no other children. With dynamic lists, we can't be sure the order is ever the same. You know, an array of random stuff. If the list of our shopping items is ever reordered, React will see that all p and input elements inside have the same type and won't know to move them. From React's point of view, the items themselves changed, not their order. The code executed by React to reorder 10 items would be something like setting the content of the nodes themselves instead of reordering them. For example, if you're doing a to-do list item thing, and you've made some temporary changes to an input in the list, and then you sort the list, you want the thing that you were in the middle of editing to still be the thing you were in the middle of editing, just moved somewhere else. The focus should be the same, the text that you've typed into the input should be the same, everything should be the same, but by default, if you don't put, we'll mention it later, if you don't put a key in your element descriptor, it won't know what to do, and it will just change the text inside of all the inputs, and suddenly you'll be in the middle of editing some other random node, which is super not what you want. If the list of our shopping items is ever reordered, React will see that all p... Oh, I already said that. So instead of reordering them, React would effectively update each of them. This can create performance issues and possible bugs. For example, the content of the first input would stay reflected in the first input after the sort, even though conceptually they might refer to different products in your shopping list. This is why React nags you to specify a special property called key every time you include an array of elements in your output. Should I use the key attribute when I'm doing an array of stuff? Probably. A key tells React that it should consider an item to be conceptually the same, even if it has different positions inside its parent element between renders. When React sees p key 42 inside a form, it will check the previous render also contained a p key 42 inside the same form. This works even if form children change their order. React will reuse the previous host instance and the same key if it exists, and reorder the siblings accordingly. Note that the key is only relevant within a particular parent React element, such as a form. React won't try to match up elements with the same keys between different parents. React doesn't have idiomatic support for moving a host instance between different parents without recreating. But, you know, why would you do it? Moving a host instance between different parents without recreating. Yeah, don't do that. So if you have an input inside of a P, and you want to move that input to being inside of a div, well, tough. It's going to recreate it. So what's a good value for key? An easy way to answer this is to ask, when would you say an item is the same even if the order changed? For example, in our shopping list, the product ID uniquely identifies it between siblings. Components. We've already seen functions that return React elements. This is the React element that it's returning, or the React element tree that it's returning. This is a function that returns a React element tree. And again, a React element tree is just a plain old JavaScript object with a certain schema, I guess. These functions are called components. They let us create our own toolbox of buttons, avatars, comments, and so on. Components are the bread and butter of React. There we go. Components take one argument, an object hash. It contains props, short for properties. Here, showMessage is a prop. They're like named arguments. And by here, they mean here. Purity. React components are assumed to be pure with respect to their props. Assumed to be pure with respect to their props. He doesn't explain what that means. So it looks like he means that props are immutable. Don't change them. In general, mutation is not idiomatic in React. We'll talk more about the idiomatic way to update the UI in response to events later. And what he means by mutation is it not idiomatic in React is that don't do it. It's bad. Everyone will hate you and think you are weird if you do that. Not idiomatic means weird. However, local mutation is absolutely fine. Do what you want. Let items equal blah. Items.push blah. Do what you want. It's your items. We created items while rendering, and no other component saw it, so we can mutate it as much as we like before handing it off as part of the render result. There's no need to control your code to avoid local mutation. There's no need to contort your code to avoid local mutation. Yeah, do what you want. It's fine. Do what you want with the stuff that you own. Your own stuff. If you're dealing with somebody else's stuff, don't mess with their stuff. If somebody gives it to you, it's immutable. If you made it for yourself, do what you want. Similarly, lazy initialization is fine despite not being fully pure. Expense form, fine if it doesn't affect other components. Supercalculator.initialize if not ready. Just, I guess, calling a random function inside of render. As long as calling a component multiple times is safe and doesn't affect rendering of other components, React doesn't care if it's 100% pure in the strictest functional programming sense of the word. Idempotence is more important to React than purity. Well, let's figure out what that means. What is an idempotent operation? Idempotent. In computing, an idempotent operation is one that has no additional effect if it is called more than once with the same input parameters. For example, removing an item from a set can be considered an idempotent operation on the set. In mathematics, an idempotent operation is one where blah, 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 blah. For example, the abs function is idempotent because abs x equals abs x for all x. These slightly different definitions can be reconciled by considering that x in the mathematical definition represents the state of an object, and f And f is an operation that may mutate that object. For example, consider the Python set and its discard method. The discard method removes an element from a set and does nothing if the element does not exist. So, mySetDiscardX has exactly the same effect as doing the same operation twice. mySetDiscardX, mySetDiscardX, Idempotent operations are often used in the design of network protocols, where a request to perform an operation is guaranteed to happen at least once, but might also happen more than once. If the operation is idempotent, then there is no harm in performing the operation 2 or more times. See the Wikipedia article on idempotence, blah, blah, blah. So in other words, a thing is idempotent if you can do it a bunch of times with the same inputs and it doesn't mess anything up. Well, not exactly, but you know what I mean. That said, side effects that are, what are we talking about, idempotence? Oh yeah. React cares if it's idempotent. Basically, a React component should be able to be called 1 or umpteen quadrillion times with the same props and return the same results, and it's fine. That's what React cares about. And by fine, doesn't like do something different each time you call it, or have a different effect, whatever. Anyway, that said, side effects that are directly visible to the user are not allowed in React components. In other words, merely calling a component function shouldn't, by itself, produce a change on the screen. Got it. Recursion. It's like cursion, but twice. Okay. Oh, now I gotta look up cursion. Is cursion a word? Recursion, a user from Canada, says the name Recursion is of English origin and means gift of God. Okay, so recursion means recursion. There's no definition of recursion. There's no recursion. There's only recursion. Okay. How do we use components from other components? How do we use components from other components? Components from components? Components are functions, so we could call them let React element equal form show message true. React dom.render React element. Can / should we do this thing? Oh, you could. However, this is not the idiomatic way to use components in the React runtime. In other words, no, do not do this thing. It is weird. People will hate you. Instead, the idiomatic way to use a component is within the same mechanism we've already seen before, React elements. This means that you don't directly call the component function, but instead let React later do it for you. Now this is pretty dang idiomatic. Anyway, the type just passes that function in as the type of this object, and then React, somewhere in its innards, will actually call it somehow, some way. And somewhere inside React, your component will be called let type equals React element.type form. Let props equals React element.props, blah, blah, blah. Let result equal type props. Component function names are by convention capitalized. Component function names, yes. When the JSX transform sees uppercase form rather than lowercase form, it makes the object type itself an identifier rather than a string. So console log, yeah. So lowercase form dot type form, uppercase form is the function. Got it. There is no global registration mechanism. We literally refer to form by name when typing form. If form doesn't exist in local scope, you'll see a JavaScript error, just like you normally would with a bad variable name. So what does React do when an element type is a function? it calls your component and asks what element that component wants to render. Asks what element that component wants to render. This process continues recursively and is described in more detail here. In short, it looks like this. You, React DOM, render app into this container. React, hey app, what do you render to? App, I render layout with a content inside. React, hey layout, what do you render to? Layout, I render my children in a div. My child was content, so I guess that goes in the div, whatever. React, hey content, what do you render to? Content, I render an article with some text and a footer inside. React, hey footer, what do you render to? Footer, I render a footer. Some more text. React, okay, here you go. I am not at all confused that footer and footer sound the same because of their capitalization. React is just hypothetics. Okay, resulting DOM structure. Div, article, some text, footer, some more text, and that's it. This is why we say reconciliation is recursive. When React walks the element tree, it might meet an element whose type is a component. It will call it and keep descending down the tree of returned React elements. Eventually, we'll run out of components, and React will know what to change in the host tree. The same reconciliation rules we already discussed apply here too. If the type at the same position, as determined by index and optional key, changes, React will throw away the host instance inside and recreate them. Inversion of control. You might be wondering, why don't we just call components directly? Why write form rather than form? React can do its job better if it knows about your component rather than if it only sees the React element tree after recursively calling them. Red circle. React has no idea layout and article exist. You're calling them. Layout, children, article. React element knows. Oh, green checkbox. React knows layout and article exist. React calls them. Layout, article. Seems the same at first, but it is very different. The difference is when these functions are called, who calls them, and fancy things that React can do if you let it call them. Fancy things. This is a classic example of inversion of control. There's a few interesting properties we get by letting React take control of calling our components. Let's look up inversion of control. Whoa, so much Wikipedia. Okay. In software engineering, inversion of control is a programming principle. Inversion of IOC inverts the flow control as compared to traditional control flow. In IOC, custom-written portions of a computer program receive the flow of control from a generic framework. Okay, that's whatever. Okay. There's a few interesting properties we get by letting React take control. Okay, what are these properties that are unique and interesting? Not necessarily unique, but interesting. Components become more than functions. React can augment component functions with features like local state that are tied to the component identity in the tree. Neat. A good runtime provides fundamental abstractions that match the problem at hand. As we already mentioned, React is oriented specifically at programs that render UI trees and respond to interactions. If you called components directly, you'd have to build these features yourself. And then, why are you using React? That's the whole point. Component types participate in the reconciliation. By letting React call your components, you also tell it more about the conceptual structure of your tree. For example, when you move from rendering feed to the profile page, React won't attempt to reuse host instances inside them, just like when you replace button with a P. All state will be gone, which is usually good when you render a conceptually different view. You wouldn't want to preserve input state between password form and a messenger chat. even if the input position in the tree accidentally lines up between them. Yes, that is a very, very good, specific example of why this is a thing. React can delay the reconciliation. If React takes control over calling your components, it can do many interesting things. For example, it can let the browser do some work between the component calls so that re-rendering a large component tree doesn't block the main thread. Interesting. Very interesting. Orchestrating this manually without re-implementing a large part of your React, of React is difficult. Yes, this is like, man, I used to try to orchestrate this manually by splitting up complex web apps into micro tasks that you could like stuff, and it was really hard. It was basically impossible because you need to rewrite your app from scratch with that concept in mind, essentially. Sneak peek beyond React 16, all this stuff. You should go watch this. A better debugging story. If components are first-class citizens, then the library is aware of, we can build rich developer tools for introspection in development. The last benefit to React calling your component functions is lazy evaluation. Let's see what this means. Lazy evaluation. When we call functions in JavaScript, arguments are evaluated before the call. Eat, prepare meal. Number 2 comes first in the source code, but actually executes second because what gets passed into it is executed first so that you can pass in the results of the thing into the other thing. So number 1, this gets computed first, prepare meal. Then with the results of prepare meal, I'm assuming the meal, you can eat it. You cannot eat an unprepared meal. That doesn't even make any sense. This is usually what JavaScript developers expect because JavaScript functions have implicit side effects. It would be surprising if we called a function, but it wouldn't execute until its results get somehow used in JavaScript. That would be super weird and confusing. And non-idiomatic of JavaScript. However, React components are relatively pure. Oh, we talked about that already. Are relatively pure. There is absolutely no need to execute it if we know its results won't get rendered on the screen. Aha! Consider this component putting comments inside it of a page. Function story with the current user. Return, type, page, props, blah, blah, blah. Okay. We're turning a page with the current user and some comments. The page component can render the children given to it inside some layout. Got it. Page. Got it. So that page there is rendering stuff with comments. Come the children, get rendered inside of the layout, etc. So a B inside of an A in JSX is the same as A children equal B. But what if it has an early exit condition? So page, current user, children. If not current user is logged in, return an H1, please log in. If we called comments as a function, it would execute immediately, regardless of whether page wants to render them or not. Aha. So yeah, so if you executed comments inside of page, then it would always render, or it would always run this function, even when you want to render something else, or even if you don't need the results, or if you're going to throw all that away, so don't do that. But if we pass a React element, we don't execute comments ourselves at all. Ta-da. Yeah, we're not executing this. We're just saying, hey, this is the thing that should be in there. And it's Page's problem to deal with. This lets React decide when and whether to call it. If our page component ignores its children prop and renders H1, please log in, instead, React won't even attempt to call the comments function. What's the point? If you're going to throw away the results, why call the function? This is good because it both lets us avoid unnecessary rendering work that would be thrown away and makes the code less fragile. We don't care if comments throws or not when the user is logged out. It won't be called. State. We talked earlier about identity and how elements' conceptual position in the tree tells React whether to reuse a host instance or create a new one. Host instances, otherwise like DOM nodes or UI element or UI hierarchy elements, like whatever, the native stuff from the host environment, the DOM, React Native, UI, whatever. Host instances can have all kinds of local state, focus, selection, input, etc. We want to preserve this state between updates that conceptually render the same UI. We also want to predictably destroy it when we render something conceptually different, such as moving from sign-up form to messenger chat. You don't accidentally message people your passwords. Local state is so useful that React lets your own components have it too. Components are still functions, but React augments them with features that are useful for UIs. Local state tied to the position in the tree is one of those features. We call these features hooks. For example, useState is a hook. Const, count, set count, useState 0. Blah, blah, blah. Later on, you can set count to some other thing, and stuff happens. It returns a pair of values, the current state and a function that updates it. The array destructuring syntax lets us give arbitrary names to our state variables. It lets us pass multiple results from the same function. For example, I call this pair count and set count, but it could have been a banana and set banana. In the text below, I will use set state to refer to the second variable or the second value regardless of its actual name in the specific example. In other words, set whatever. You can learn more about useState and other hooks provided by React here. And here is a link to some other thing. Checking mouse. Consistency. Even if we want to split the reconciliation process itself into non-blocking chunks of work, we should still perform the actual host tree operations in a single synchronous swoop. This way, we can ensure that the user doesn't see a half-updated UI and that the browser doesn't perform unnecessary layout and style recalculation for intermediate states that the user shouldn't see. The user shouldn't see it. This is why React splits all work up into the render phase and the commit phase. Render phase is when React calls your component and performs reconciliation. It is safe to interrupt and in the future will be asynchronous. In the future, right. Commit phase is when React touches the host tree. It is always synchronous. React touches the host tree. That means React itself, the innards of React are actually applying the changes that you have described to the actual host environment by creating DOM nodes, changing properties on existing DOM nodes, or in the React DOM environment, or in React Native, that would be instructing the native innards to create and destroy and update native UI view things. That is the commit phase when React touches the host tree. It's always synchronous. Memoization. Okay, first I'm going to do a thing right quick. Just going to tell Dan that I am currently in the process of reading his thing if he wants to watch. Oh, Danny boy, this link you must be clicking it. Anyway. Memoization. It's the isationifying of memos. When a parent schedules an update by calling setState, by default, React reconciles its whole child subtree. And by reconciles, it means it's doing all the things, part of the stuff, doing stuff. This is because React can't know whether an update in the parent would affect the child or not. And by default, React opts to be consistent. That's good. This may sound very expensive, but in practice, it's not a problem for small and medium-sized subtrees. When trees get too deep or wide, you can tell React to memoize a subtree and reuse previous render result during shallowly equal prop changes. Oh my, that was quite a mouthful there. Okay, let's see. What do you mean by memoization? Not to be confused with memorization, which is exactly the same except for that one letter. In computing, memoization or memoization is an optimization technique used primarily to speed up computer programs by storing the result of expensive function calls and returning the cached result when the same input occur again. Memoization has also been used in other contexts and for purposes other than speed gain, such as in simple mutually recursive dispersion. Although related to caching, memoization refers to a specific case of this optimization, distinguishing it from forms of caching such as buffering or paid replacement. In the context of some logic, so, long story short, to memoize is to remember the result of calling a function, and then when instead of actually calling the function again the next time that you want the same results, just passing back the same results as is without calling the expensive thing. So if your function is, hey, calculate pi, that might take a while, so just keep track of the result when you finally get the result of pi calculated. Then every time you are told to calculate pi again, just, I already remember pi, so I don't need to calculate pi. So then I guess you should name your function getPi instead, and then it will only calculate it if necessary. If you name a function calculate, it better calculate every single time. Naming matters. Anyway. When trees get too deep or wide, you can tell React to memoize a subtree and reuse previous render results during shallowly equal prop changes. Shallowly equal prop changes. What is a shallowly equal prop change? What does shallowly equal mean? What is a prop change? What is a prop? So a prop is a single item in the props object. So the props object is a key value object of keys, the name of the prop property, and value, which is some random thing. Those two props objects are shallowly equal if each of the values of each of the keys of each of the objects matches. And by matches, shallowly, that means it is not a deep comparison. So if you have object A and object B, if they do not 3 equals one another, if they are not literally the same exact object, then they're not shallowly equal. Deep equal would be to, I don't know what they're saying, let's like recur through them and see if all of their properties and blah, blah, blah match, yada, yada, yada. So shallowly equal. So when subtrees get too deep or wide, you can tell React to memoize a subtree and reuse previous render results during shallowly equal prop changes. Okay, so if I So if you're re-rendering the React thing, set state or whatever, and it's re-rendering a thing, if the props passed into a component are the same, shallowly equal, then you can optionally and explicitly tell React to use the same result each time by doing this thing we're about to say, and that is memoization of React element subtrays. Okay. There's a lot of complexity in that one sentence. Anyway, so what do? We say react.memo of this thing, and it creates a new thing that memoifies that thing. Yay. So now set state in a parent table component would skip over reconciling rows whose item is referentially equal to the item rendered last time. Oh man, that's a confusing mouthful. So in other words, if you pass the same item into row every time, you can, so if you want to render the same result when you pass item into row every single time, if you know for sure, this is always going to render the same exact output every single time the inputs are the same, you can tell it to remember the results and reuse them, but it would be a waste of time if row is not terribly expensive. Maybe. Let's see. Now, if the parent or the owner of the row, for example, a table component, so if that thing did a set state and therefore the table is going to re-render, normally it would, re-render all these guys too, but if the inputs are exactly the same, or, referentially equal, then it's just going to reuse the same exact result and not even call this again. Right, okay. That's... Okay. You can get fine-grained memoization at the level of individual expressions with the useMemo hook. The cache is local to component tree position and will be destroyed together with its local state. It only holds one last item. Okay, that is pretty cool and super useful, but you're probably not going to use that super often. React intentionally doesn't memoize components by default. Many components always receive different props, so memoizing them would be a net loss. So React isn't going to shoot its own self and you in the foot by trying to be too smart by default. Just gives you the power and lets you figure it out. Raw models. Ironically, React doesn't use a reactivity system for fine-grained updates. Haha! In other words, any update at the top triggers reconciliation instead of updating just the components affected by changes. This is an intentional design decision. Time to interactive is a crucial metric in consumer web applications, and traversing models to set up fine-grained listeners spends that precious time. Okay, that requires a lot of context to understand this sentence. So, let's get that context right now. So, React was originally created and intended for use on the web. On the web, you really, really care about how quickly stuff loads. And the way in which you determine whether a thing is actually loaded is, can I use the thing? If it's just content, is can I see the content? If it's like an app or something, can I use the app? Can I do a thing? Can I interact with it in some useful way? So the metric that you care about when you care about the performance of a app is the time that it takes to become interactive. This is called time to interactive. So time to interactive is a crucial metric. It's absolutely crucial that you track this thing and optimize your stuff to target this metric of consumer web applications. And traversing, okay, so what does this have to do with what? What are we talking about? So reactivity would be bad for time to interactive. Why? Because traversing models to set up fine-grained listeners spends that precious time. So this insinuates or implies that reactivity would require traversing models to set up fine-grained listeners, which is a phrase that who cares what it means? It is a waste of time when you care about that, basically. In other words, you're doing way too much work when the page loads. You don't need to do that right now. Do it later. React does it later. Got it. Additionally, in many apps, interactions tend to result either in small, button hover, or large page transition updates, in which case fine-grained subscriptions are a waste of memory resources. So reactivity, doing like data binding and stuff like that, is a waste because most apps just don't need that kind of stuff. It's like you use it so minimally, but you do so many other types of little or huge changes that it's best to optimize for the common case. That's what React does, and that's why it is good, and we love it. One of the core design principles of React is that it works with raw data. React works with raw data. Vegan data. If you have a bunch of JavaScript objects received from the network, just a bunch of random stuff, you can pump them directly into your components with no pre-processing. There are no gotchas about which properties you can access, no unexpected performance cliffs when a structure slightly changes. React rendering is view size rather than model size. And what he means by that is the operation happens, the number of times or the speed at which the operation happens is dependent on the size of the view, not the size of the model. So in other words, if your view is if your view is huge, the operation will take a while, like rendering and stuff. But if your model size is huge, it doesn't care. It cares about your view size, doesn't care about your model size. And you can significantly cut the view size with windowing. Ooh, windowing. React window. What does that mean? So you got like infinity things in this list, but we're only actually putting 9 of them in the DOM. Neat. So that will make things better by doing this. This is called windowing, where you play some fun tricks with the DOM so that you can make things fast. And the specific trick that you're playing is to only render the stuff that you see and to not render the infinity of other things that you do not see. So that when you scroll, it's changing the contents of the things that you see instead of just actually scrolling the list of infinity things, because a list of infinity things would be infinitely huge and infinitely expensive and infinitely bad. And it would make us all infinitely sad. Anyway, time to interactive, focusing on the human-centric metrics. Okay, now look that up in your own time. There are some kinds of applications where fine-grained subscriptions are beneficial, such as stock tickers. Yes, if you've got a stock ticker app, maybe handle those updates in some special way. This is a rare example of everything constantly updating at the same time. While imperative escape hatches can help optimize such code, React might not be the best fit for this use case. Still, you can implement your own fine-grained subscription system on top of React. Go for it. Note that there are common performance issues that even fine-grained subscriptions and reactivity systems can't solve. For example, rendering a new deep tree, which happens at every page transition, without blocking the browser. Change tracking doesn't make it faster. And reactivity and change tracking, these are the same things. Roughly speaking, they're the same. So, data binding, reactivity, setting up things so that stuff happens when stuff changes. All that stuff is a huge waste of time when you're just first loading the thing. When you just first load the thing, you want it to be ASAP. So if you do any extra work at all during that, it is a huge waste of time, and you are hurting your users and making everyone sad, and making us all lose money and time. But if you're doing something like a stock ticker thing, like, you should probably do that. Because who cares if it loads half a second slower or whatever? You want every single update to be like ASAP or whatever. Change tracking doesn't make it faster, doesn't make page loading faster. It makes it slower because we have to do more work to set up subscriptions. Another problem is that we have to wait for data before we can start rendering the view. That's a problem. In React, we aim to solve both of these problems with concurrent rendering. You should totally check out all this stuff. Batching. Man, how much of this article is there? Oh boy. How long have I been doing this thing? 1 hour and 8 minutes and 33 seconds. Batching. Several components may want to update state in response to the same event. This example is convoluted, but it illustrates a common pattern. You got your parent, you got your child. Rendering the child and the parent inside of a div. And then when you click on the div, it sets the count to 1 more. And then it changes this text to include the count. And then the child, what happens with the child? Several components may want to update state in response to the same event. This example is convoluted, but it illustrates a common pattern. Okay. And then when you click the button inside of the child, it sets the count inside of the child more than 1. Okay, so the thing that we care about is that when you click this button on the screen, it is going to run this onClick, which sets this state, and it's going to run this onClick, which sets this other state. So in other words, 2 states are being updated with 1 click. This example is convoluted, sure, but it illustrates a common pattern, which is several components may want to update state in response to the same event. Okay, so the same event is clicking this button, and then several components may want to update state. So 2 separate components are updating state based on that 1 click. Okay. When an event is dispatched, click, the child's onClick fires first, this one, triggering its set state. Then the parent calls set state on its own onClick handler. Here. If React immediately re-rendered components in response to set state calls, we'd end up rendering the child twice. No bueno. Entering React's browser click event handler. Click. Child, onClick, set state, re-render child, unnecessary. Parent, onClick, set state, re-render parent, re-render child. Oh no, we re-rendered child twice. Exiting React browser click event handler. Okay. The first child render would be wasted. Like, why are you doing all this? And we couldn't make React skip rendering child for the second time because the parent might pass some different data to it based on its updated state. So doing it the first time was wasted because we have to do it the second time. We have to do it the second time because of reasons. And since we have to do it the second time, there's no need to do it the first time. So we might as well just do it once. Do it then. So if you had a purely reactive rendering system that re-rendered everything every time you set any state at all, it would render too much. And it would be bad and slow. And everyone would be sad. The first child render would be wasted, and we couldn't make React. Okay. I can wait a second. Right. This is why React batches updates inside event handlers. Entering React browser, click event handler. Child, on click, set state, and then nothing. Parent, on click, set state, processing state updates. Re-render parent, re-render child. Exiting React browser, click it. The set state calls in components wouldn't immediately cause a re-render. Instead, React would execute all event handlers first, and then trigger a single re-render, batching all those updates together. This is a good thing. Batching is good for performance, but can be surprising if you write code like this. Can be surprising if you write code like this. Okay. I think he's going to explain why. We don't have to figure it out. If we start with count set to 0, these would just be 3 set count 1 calls, right? You know, if count is 0, then set counter count plus 1 is going to be 0 plus 1 every time. So this is set counter count plus 1. So this is set counter 0 plus 1, 0 plus 1, 0 plus 1. Yeah, that's not useful. To fix this, set state provides an overload that accepts an updater function. Aha! Updater function. Okay, so ba-doom. So instead of figuring out the results before passing it into the setter, we pass a function that lets the setter figure it out later. React would put the updater functions in a queue and later run them in sequence, resulting in a re-render with count set to 3. Because it would render the first time with C, pass in the current value of set state, which by default would be 0, which then that C would be 0, and then so increment would call increment set counter, and it would queue up 3 of these guys, and then these would be run in sequence with the results of running the previous one. Neat. Okay. When state logic gets more complex than a few set state calls, I recommend to express it as a local state reducer with the use reducer hook. No, I clicked instead of... I lost my scroll state. Oh, man. Hey, pro tip for all the people making websites. If you have a link on your page and somebody clicks that link and then they hit the back button, your website should be exactly the same pixel for pixel as it was when they clicked that link. If it's not, it is bad. Anyway, I recommend to express it in a local state reducer with the use reducer hook. It's like an evolution of this updater pattern where each update is given a name. Yeah, so it's kind of the same thing as doing this, but instead of calling a function named increment, you just tell it, hey, do a thing called increment. However you want to do it, just do this thing called increment, just do it. The action argument can be anything, although an object is a common choice. And the action argument, action equals increment, and then it does the thing. Call tree. A programming language runtime, it usually has a call stack. When a function A calls B, which itself calls C, Somewhere in the JavaScript engine, there's a data structure like ABC that keeps track of where you are and what code to execute next. Once you exit out of C, its call stack frame is gone. Poof. It's not needed anymore. We jump back to B. By the time we exit A, the call stack is empty. Of course, React itself runs in JavaScript and obeys JavaScript rules, but we can imagine that internally React has some kind of its own call stack to remember which component we are currently rendering. For example, app page layout article, we're here. React is different from a general purpose language runtime because it's aimed at rendering UI trees. These trees need to stay alive for us to interact with them. The DOM doesn't disappear after our first React DOM render call. That would be, silly. This may be stretching the metaphor, but I like to think of React components as being in a call tree rather than a call stack. When we go out of the article component, its React call tree frame doesn't get destroyed. We need to keep the local state and references to the host instance somewhere. And the link to somewhere is the how and why of React's usage of linked lists in Fiber to walk the components tree. Okay, not today. Not today. Someday. Anyway, these call tree frames are destroyed along with their local state and host instances, but only when the reconciliation rules say it's necessary. If you ever read React source, you might have seen these frames being referred to as fibers. Aha! Fibers are where the local state actually lives. Fibers are... What are fibers? Fibers are where the local state actually lives. Aha! When state is updated, React marks the fibers below as needing reconciliation and calls those components. Okay, this is starting to get complicated. Okay, so these call tree frames are destroyed. So you got call tree frames. You got a tall call tree frame. Okay. You got a call tree frame, not a call stack. Call stack. It's destroyed as you go up the stack. Call tree keeps it around. Call tree. Its React call tree frame doesn't get destroyed. Okay. These call tree frames are destroyed along with their local state and host instances, but only when the reconciliation rules say it's necessary. So they don't automatically get destroyed like in a call stack. They get intelligently destroyed because it's a call tree. Trees are awesomer than stacks. Haha. If you ever read React source, you might find these frames being referred to as fibers. Okay, I see. Okay, got it. Fibers where the local state actually lives. Okay. So you got a thing called a fiber. It keeps track of the stuff and the things. Anyway, who cares? Next, context. In React, we pass things down to other components as props. Sometimes the majority of components need the same thing. For example, the currently chosen visual theme. It gets cumbersome to pass it down through every level. In React, this is solved by context. It is essentially like dynamic scoping for components. Dynamic scoping? What is dynamic scoping and lexical scoping? Scoping itself is how you search for a variable with a given name. A variable has a scope, which is the whole area in which the variable can be accessed by name. If there is a reference to a variable A, then how does the compiler or interpreter find it? In lexical scoping, and if you're the interpreter, I'm the interpreter. I'm going to search in the local function which is running now. Then I'm going to search in the function or scope in which that function was defined. Then I'm going to search in the function scope in which that function was defined, and so forth. Lexical here refers to text, in that you can find out what variable is being referred to by looking at the nesting of scopes in the program context. In dynamic scoping, by contrast, you search in the local function first, then you search in the function that called the local function. Interesting. Then you search in the function that called that function, and so on, up the call stack. Dynamic refers to change, in that the call stack can be different every time a given function is called. And so the function might hit different variables depending on where it is called from. I see. So dynamic scoping versus lexical scoping. Lexical scoping is kind of like JavaScript itself. So if you have a function and a function and a function and a function, and the deepest inner function says, for example, window.alert howdy, then JavaScript, the runtime, the engine, V8, whatever, when it sees the word window, it's like, I don't see a window inside of this function. So then it goes to the parent function in which that currently running function was defined. In other words, like your source code. And it says, where's the window? And it keeps going up and up and up in the stack of where the functions were defined when you like wrote them down. That is lexical scoping, and that is how JavaScript handles variable lookup. But dynamic scoping, Alexa is unconvinced. Alexa, shut up. I hate to be rude to Alexa, but anyway. Where was I going? Oh, right. So dynamic scoping is a thing that does not exist in JavaScript. At least not encoded in the syntax of it, whereby if you wanted to have a function that looked up the value of, for example, window every single time that that function is run, you would have to pass a function into that function that did that thing. Okay. So it's possible to do something that looks like dynamic scoping if you squint in JavaScript, but it's not a thing you have to worry about happening on accident. Okay. In React, this is solved by context. It is essentially like dynamic scoping for components. Aha. Now we know what that is. Dynamic scoping. So it's going to look up the value of that thing by name based on where it was called, not where it was defined. Cool. It's like a wormhole that lets you put something on the top and have every child at the bottom be able to read it and re-render when it changes. That was not clear. Let's see a specific example, and then it shall become clear. So we got a dark app. This app is dark because it provides the value of dark for the theme and then renders a bunch of stuff. So inside of the bunch of stuff, something way down into the bowels of the stuff uses the theme context, and therefore this value will be dark when this some deeply nested child is inside of a thing that provides the value of dark for that context, thereby implementing dynamic scoping, which we now understand. So the opposite of like dynamic scoping, lexical scoping here would be like const theme equals, actually I guess it would just be delete this and then use the word theme in here somewhere, and then inside of your source code just do like const theme equals dark in your source code. Doing it dynamically requires you to like write some code, because that's how JavaScript works. Got it. Okay, let's read through what Dan wrote. When some deeply nested child renders, this guy, use context theme context will look for the closest theme context provider, this one, above it in the tree, and use its value above it in the tree. And in the tree is in the render tree, the element tree, the component hierarchy tree, that thing. In practice, React maintains a context stack while it renders. If there's no theme context.provider above, the result of use context theme context call will be the default value specified in the create context call. In our example, it is light. Effects. We mentioned earlier that React components shouldn't have observable side effects during render. But side effects are sometimes necessary. We may want to manage focus, draw on a canvas, subscribe to a data source, and so on. In React, this is done by declaring an effect. Declare your effect. What effect does this have? It has this effect. I'm going to use this effect in this component. What is an effect? It is a thing that you make happen. You have cause and effect. Okay, so why did this effect happen? Cause use effect said it should. Okay. In React, this is done by declaring an effect. When possible, React defers executing effects until after the browser repaints the screen. This is good. Why? Because code like data source subscriptions shouldn't hurt time to interactive and time to first paint. Those metrics. The time that it takes to load a page should not be dependent on doing unnecessary things. But you want to do those necessary things at some point, so do them as soon as possible, which is as soon as the site becomes interactive and paints. There's a rarely used hook that lets you opt out of that behavior and do things synchronously. Avoid it. Rarely used. What is it? Use layout effect. Basically, you probably don't need this, but if you know you do, then there it is. And now pretend you don't know you do. Unless you do. Effects don't just run once. Effects run both after component is shown to the user for the first time and after it updates. Effects can close over current props and state, such as with count in the above example. Close over. This is a concept that we will describe in a second. Such as with count in the above example. Effects may require cleanup, such as in the case of subscriptions. To clean up after itself, an effect can return a function. So first, let's talk about close over. So to close over is referring to lexical scoping. Boom. So count. So when this function gets run sometime later, how do we know what count is? Also, how do we know what document is? So the count, we know, well, it's not inside this function. So the JavaScript runtime looks outside of it to where it's defined. Remember, this is lexical scoping, not dynamic scoping. So just look up to, boom. That is the text, the same text. Boom, count and count. Therefore, the value of count is whatever this function returned when this function was defined. And notice this is an inline function. We're defining it inline right after getting the state. So later on, when this function is called, it will still, count will still be the same as it was when this function was defined. It cannot change. Or, you know, it won't change, whatever. Right. So that's what it means to close over. So it closes over this value by declaring the function right after it, which is in the lexical scoping sense of the word. Whatever. Anyway, next. Close over. Right, okay. Now clean up. Return a function from a use effect. Can return a function. React will execute the return function before applying this effect the next time, and also before the component is destroyed. Sometimes rerunning the effect on every render can be undesirable. You can tell React to skip applying an effect if certain variables didn't change. So, we want to have this effect. What effect? We want to change the title of the document. What document? The current document, as defined by lexical scope. We want to change the title to you clicked count times. What is count? Well, at first 0 times. So first time it renders, later on React is going to call this function, which is going to execute this code, which is going to set the title of the current document to you clicked 0 times, because the value of count was 0 when this function was defined. Now, when do we run this again? So now say we set some other random state or some other thing happened and we're re-rendering this stuff, but count's still the same. Do we want to run this code again? Do we want to set document.title, you clicked 0 times, you clicked 0 times, hey, you clicked 0 times. I'm like, stop telling me I clicked 0 times, I already know. Click 0 times, I get it. We get it. Stop telling me. It's fine. How do you do that? How do you get it to leave you alone until it actually changed the thing? Well, you clicked 1 times. Well, I want to know that. Please let me know. But don't tell me about the 0 times ever again. Unless you have to. Unless I don't know. Anyway, how do you do that? You pass it in as an array to useEffect. Why do you do that? So that it will do the thing we just said. Or, avoid doing this thing unless this thing changes. Basically, this array here defines all the things that you care about in this code. However, it is often a premature optimization can lead to problems if you're not familiar with how JavaScript closures work. For example, this code is buggy. So, use effect, data source, add subscription handle change. And then return function, data source, remove subscription handle change. So, what's the problem here? We're only doing this once. Let's see. Why is this buggy? Let's find out. It is buggy because empty array says don't ever re-execute this effect. But the effect closes over handle change, which is defined outside of itself. Lexical scoping. Yay, lexical scoping. I feel like such a nerd when I say lexical scoping. Well, it's just because of lexical scoping. You know how it is. When you're scoped lexically, whatever. But the effect closes over handle change, which is defined outside of it. And handle change might reference any props or state. Who knows? Who knows what handle change is, what it does. This effect don't know. Alright, it's closing over it. Double it. So, if we never let the effect rerun, handle change will keep pointing at the version from the first render, and count will always be 0 inside of it. To solve this, make sure that if you specify the dependency array, it includes all things that can change, including the functions. All the things. So, inside of the function, your useEffects function, what goes in this array? Everything that can change. All the things in here that can change. Everything. All of the things, each of the ones. Depending on your code, you might still see unnecessary resubscriptions because handle change itself is different on every render. The use callback hook can help you with that. Alternatively, you can just let it resubscribe. For example, browser's add-event listener API is extremely fast, and jumping through hoops to avoid calling it might cause more problems than it's worth. You can learn more about useEffect and other hooks provided by React here. Custom hooks. Since hooks like useState and useEffect are function calls, we can compose them into our own hooks. Yeah. Your own custom hook. Use window width. And you got a bunch of stuff. Instead of putting all this stuff here, you can put it over here, and then reuse it a bunch of times. Custom hooks let different components share reusable stateful logic. Note that state itself is not shared. Each call to a hook declares its own isolated state. You can learn more about writing your own hooks here. Static use order. Static use order. What does that mean? You can think of useState as a syntax for defining a React state variable. It's not really a syntax, of course. We're still writing JavaScript, but we are looking at React as a runtime environment. And because React tailors JavaScript to describing UI trees, its features sometimes live closer to the language space. If use was a syntax, it would make sense for it to be at the top level. Note, not a real syntax. Component example const count. Set count equals use state 0. What would putting it into a condition or a callback or outside of a component even mean? What are you talking about? Sorry, I got confused. Okay. Alright, you can think of useState as a syntax for defining a React state variable. A React state variable. Not really a syntax, of course, we're still writing JavaScript. So he's talking about some imaginary language that does not exist. With different syntax from JavaScript that has a use, a keyword called use, that when using using the use keyword in this imaginary language, it would do what now? It would define a React state variable. And that means what now? We're still writing JavaScript. We're looking at the what? Okay. So in this imaginary non-JavaScript language, calling this imaginary non-JavaScript keyword use would do what? It would define a React state variable. Okay. Sure. And what would putting it into a condition or a callback or outside of a component even mean? Note, not a real syntax. So in this imaginary non-JavaScript syntax, this is a local state of what? Use state of what? What is this? A state of? If condition, what happens to it when condition is false? And this does not at all make anything clear. Thinking of things in the context of an imaginary non-JavaScript language does not at all help me understand anything. I'm sorry. It's just more confusing. Sorry, Dan. Anyway, React state is local to the component and its identity in the tree. If use was a real syntax, it would make sense to scope it to the top level of a component too. So I think his imaginary syntax is wrong. You wouldn't want const, you'd want use. It would replace const. Because it wouldn't make sense to put const inside of a conditional, because then you can't use it outside of the condition and stuff. Anyway, this is similar to how import only works at the top level of a module. Of course, use is not actually a syntax. It wouldn't bring much benefit and would create a lot of friction and confusion. However, React does expect that all calls to hooks happen only at the top level of a component and unconditionally. The way that that Ryan Florence, RPFlow, says it is that we love React hooks. In fact, we love them unconditionally. So do not put your use whatever function calls into any kind of condition, like if or a for loop or anything like that. It will break the world because of reasons. These rules of hooks can be enforced with a linter plugin. You should use that thing. It will make you happy. Or actually, I guess it will make it harder to make you sad. There have been heated arguments about the design choice, but in practice, I haven't seen it confusing people. Yes, your explanation of it is more confusing than the actual implementation. I also wrote about why commonly proposed alternatives don't work. I am not going to read that. Internally, hooks are implemented as linked lists. Fun fact. When you call useState, we move the pointer to the next item. When we exit the component's call tree frame, we save the resulting list there. Where? A linked list. Until the next render. Neat. I knew linked lists were good for something, not just making people scratch their heads in interviews. I wonder what percentage of linked lists are used on whiteboards versus in reality. It's probably some percentage, probably 37.2%, which is coincidentally the exact same percentage of percentages that are made up on the spot. Anyway, this article provides a simplified explanation of how hooks work internally. I'm going to read that, yes. Arrays might be an easier mental model than linked lists. Yes. This is not real code. This is pseudocode, but it is JavaScript. Wait, is it? No, pseudocode. Not JavaScript, but it's JavaScript-ish. Pseudocode. Let hooks and I create these variables. Define this function that we'll look at later. Prepare to render. I equals -1. Hooks equals fiber.hooks or empty array, whatever. Wait, where are we getting this fiber from? Where does this fiber come from? Lexicals, whatever. What was it? What were we talking? Okay. Lexical. Whatever. It's getting it from code that you do not see here. Okay, so fiber.hooks or an empty array. So this, we're talking about the implementation of hooks. That is the point. This function here is an imaginary implementation of useState, which is internal React innards. So hooks equals, what do we want? Hooks, like the result of whatever this, some array full of something. Call your component here, your component gets called, okay. Remember the state of the hooks. Fiber.hooks equals hooks. Okay, so we define hooks up here. So hooks equals fiber.hooks for this. Okay, so we're redefining we're changing the value of hooks here to be either either fiber.hooks or an empty array. Then we're calling the function. Then we're remembering, we're keeping track of this. So basically, your component may or may not mutate hooks, which is an array of something. So we've got this mutable array that your component may or may not mutate, and we're keeping track of it. We're keeping track of it in a fiber. In other code that is not defined here. So useState. Now, what happens in useState? So your component may or may not call useState 0 or more times. And what happens? Well, then, wait, I'm not even using this anywhere. Why? Oh, wait, we're using it here. Okay. All right, so the first time that this gets called, the current index is set to -1. This is somewhere preparing to render your component. Remember, this is inside of some imaginary pretend implementation of how hooks work, React hooks. So when calling your code, before calling your code, React makes a thing called a fiber. And the thing called a fiber has an array on it called hooks. And before calling your component, it grabs a local array called hooks and sets it to either the hooks from before or new. And then after running your component, it will remember the results of whatever the local hooks changed to. And use state, when run from inside of your component, will modify the local copy of hooks because of lexical scoping or whatever. Haha. Anyway, so right, so it will only do this once for each execution of the thing. And the first render, got it. So use state only does the first thing once, and then every other time it just returns the results of the first thing. All right, whatever. Okay. If you're curious, the real code is here. We'll look through that someday later, probably not. This is roughly how each use state call gets the right state. As we learned earlier, matching things up isn't new to React. Reconciliation relies on the elements matching up between renders in a similar way. What's left out? We've touched on pretty much all important aspects of the React runtime environment. If you finish this page, I haven't yet, but I'm close, you probably know React in more detail than 90% of its users. And there's nothing wrong with that. Why would there be something wrong with that? Or maybe that's the joke. There's nothing wrong with that. Yeah. Maybe it needs an emoji so you can tell. Typography and voice intent. It's hard to... Anyway, whatever. There are some parts I left out. Damn. Left out. Mostly because they're unclear even to us. React doesn't currently have a good story for multi-pass rendering. In other words, when the parent render needs information about the children. Also, the error handling API doesn't yet have a hooks version. It's possible these two problems can be solved together. That'd be neat. Concurrent mode is not stable yet. And there are interesting questions about how suspense fits into this picture. Maybe I'll do a follow-up when they're fleshed out and suspense is ready for more than lazy loading. I think it speaks to the success of React's APIs that you can get very far without ever thinking about most of these topics. Good defaults like the reconciliation heuristics do the right thing in most cases. Warnings like the key warning nudge you when you risk shooting yourself in the foot. If you are a UI library nerd, I would like to consider myself. I hope this post was somewhat entertaining and clarified how React works in more depth. Or maybe you decided React is too complicated and you're never looking at it again. That's fine. In either case, I'd love to hear from you on the Twitters. Thank you for reading. You're welcome for reading. I think we should discuss this on Twitter. Thank you, Dan Abramov. And now I think that's it. Good night, everybody.